Hey everybody. So today we're going to be talking about molecular orbital theory diagrams for heteronuclear diatomics. We've done a lot of diagrams where the two atoms were the same. So here we're going to do heteronuclear, so you've got two different atoms, but still diatomics is still only two atoms in our diagram. So here we go. So because you have two different atoms, you're going to have asymmetric molecular orbital diagrams. And the reason you're going to have asymmetric, so you're going to have an asymmetric diagram because you've got different atomic orbitals and energies on the two different atoms. In the previous case, we had like an oxygen with an oxygen, so they're going to have the same basic set to work with. But now if we switch to a nitrogen and an oxygen, those orbitals are a little bit different. The energies of those orbitals are different because they have different amount of pull on the electrons in the nucleus. And so what you're going to see are atoms with a greater Z effective. So this is an idea from 127. The effective nuclear charge. So that's the charge an electron actually experiences, takes into account shielding and things like that. So the atoms that have that greater pull from the nucleus will pull the electrons closer. As a result, they'll have a more stability in those orbitals, and then they're going to lower the energy there. All right, so we only got two structures to look at. So let's look at two diagrams, I should say. All right, so here's the first diagram. It's for hydrogen fluoride. So on one side is hydrogen, on the other side is fluorine. So take a minute, draw your picture here, pause the video, and then come back. So notice on the left is the hydrogen, on the right is the fluorine. Fluorine, very electronegative, really pulls on those electrons and hugs them close. Because of that high electronegativity, these 2p orbitals that would be the ones involved in bonding are very low in energy. So we've got highly electronegative fluorine, pulls the electrons really close. And then hydrogen with this just one s orbital doesn't pull nearly as strong as that fluorine, so it's going to be higher in energy. Okay, when you think of hydrogen and fluorine, you think of a Lewis structure that looks like this. You're only anticipating, if you think of a Lewis structure, a single bond and a single connection. And hydrogen only has the one electron to offer up. So when you do your MO diagram, what we do here is we take one of the orbitals from S, and we take one of the p orbitals here. One of the s orbital from hydrogen, the p orbital from fluorine, that are both short-handed here and missing an electron. And these two get combined to make my new molecular orbitals, a sigma and a sigma star. Notice we don't say sigma s or sigma p because it's a mix of s and p made together to make that, but it is a bonding and an anti-bonding. Then the electron from hydrogen and the electron from fluorine can hang out in that lower energy bonding molecular orbital. Then we have these two guys here from fluorine that nothing happened to them. They did not mix with the hydrogen. They are just non-bonding molecular orbitals, so they just sort of stay put. They are still present on the fluorine. Now, notice that this molecular orbital of fluorine is closer in energy to fluorine, which means these electrons spend more time or have a higher probability near the fluorine, which makes sense between hydrogen and fluorine. Fluorine is more electronegative, and those electrons are going to get pulled. So these electrons here are getting pulled towards fluorine, and we see that in the energetics. Likewise, this anti-bonding molecular orbital is up here, and it's closer in energy to hydrogen. So if we had any electrons in that anti-bonding molecular orbital up here, they would spend more of their time near hydrogen because that's a better energy match. All right, let's try one more. Let's try nitrogen and oxygen. Now this one gets a little tricky because nitrogen and oxygen are sort of that divider. Nitrogen's on one side and gets a certain molecular orbital diagram, and oxygen's on the other side and gets a different molecular orbital diagram. So the question is, which molecular diagram do we pick? In this case, it doesn't matter, and I'll show you why. So nitrogen would get the one with orbital mixing, and oxygen would get the one without orbital mixing. So the diagram I've got drawn here is the one with mixing, where the sigma 2s and the 2s star get pushed down in energy, and then the sigma 2p and the sigma 2p star get pushed up in energy, and then those two right here reverse. So we're showing the picture with mixing right now. All right, other things to look at and notice. So on the left, we've got nitrogen. On the right, we've got oxygen. Oxygen's more electronegative. So his orbitals are stabilized and a little lower in energy than nitrogen's. So notice the S of the nitrogen of the oxygen is a little bit lower than the S of the nitrogen, and the same thing in the P. Nitrogen has its 5 valence electrons, oxygen has its 6. We still are going to mix them and fill up the same, get a similar molecular orbital diagram with the sigma 2s, the sigma 2s star, and that kind of pattern that we see here. The thing I want to notice here, with mixing or without mixing, it's right here. The change would either be this direction or reversed, but in either case, it's all full in either version. So in the nitrogen-oxygen case, whether you pick mixing or not mixing, you're going to get the same answer. The bond order is going to be the same. The paramagnetic or diamagnetic is going to be the same, because these 6 orbitals right here in the middle would be all filled. Doesn't matter the order if it was reversed or not reversed. So there we go from our nitrogen-oxygen perspective. The last little detail here, if you wanted to look at this lonely electron up here, that lonely electron, if you look, where would you anticipate it spending more of its time? Notice in terms of energy, it's a closer in energy here. And if you draw the Lewis structure for NO, it looks something like that. So that one little dot right there, notice it's on the nitrogen. So there you go, a little information about molecular orbital diagrams when the atoms are not the same. Look for that asymmetry, lower the one that's more electronegative, and then sort of fill in your diagram from there.